Welcome everybody to the AMS Colloquium. I am your host, Assistant Professor Paul Constantine. Sorry, what just happened here? Really excited about today's colloquium, as long as this works out. Yep, okay. Let's just make sure, as we're getting started here, that doesn't happen. With energy saver, all the way. Earth, energy, and environment, right? Very excited about today's colloquium. We have Professor Dennis Cook from University of Minnesota to tell us about envelopes and envelope methods. Also really excited because our AMS Colloquium correspondents are going to do a profile of someone that you all know and love, our president Paul Johnson, who came to visit us for colloquium. So everybody say hi to Paul. Hi, Paul. All right, and with that, I will turn it over to our AMS Colloquium correspondents, Jessica Daters and Izzy Aguiar, to talk about President Johnson. Jessica and Izzy.
Hi, everyone. We're excited to actually be live with you this week. Still 100% confident that we're live. What'd you say?
Yeah. And we're 100% confident that I'm Izzy and this is still Jessica.
Yeah.
So, yeah.
No need to discuss the confidence intervals this time, I'm sure you know.
It's science.
So as Dr. Constantine said, we had the extreme honor of getting to sit down and interview our president, Dr. Paul Johnson, earlier this week. We just wanted to clarify, just in case some of you don't know, the kids call him PCJ. So if we refer to him, that's still Dr. Johnson.
So one of our favorite parts about being the correspondents is that we get the opportunity to sit down with people that we really admire and look up to. And we get to sit down and ask you about your life and ask you about how you got here, and in a way humanize the professors that we kind of view as amazing.
Yeah, so which leads us into something new that we're starting out. I don't know if any of you know what StoryCorps is, but it's this really great podcast project that emphasizes the power of listening and the power of sitting down and hearing stories and learning from those stories. So if in the future we ask to sit down with you and talk with you, we are going to be probably using the StoryCorps app. So we did it with Dr. Johnson this week. It's this really great app. It gives you interview question suggestions, and it also records the whole interview. And at the end of the interview, you can upload it to the Library of Congress. So Dr. Johnson is officially immortal in the Library of Congress. So if any of you want to hear our raw interview as well, let me know and I can direct you towards it. But yeah, so StoryCorps and Jessica and I really do have like the same values of understanding people on this human level, getting the opportunity to speak with these role models and really sit down and listen with them.
So some of you might be wondering why we're profiling PCJ at the Math Colloquium. So we wanted to give you a little bit of background on his math career. So while PCJ wasn't a math major, we did learn that he has developed a passion for math. And I say developed because in high school, math wasn't necessarily his favorite subject, which some of us might relate to. I know I've talked to a couple of professors who say math didn't make sense until the numbers were gone. But he said that he really developed his passion for math in college, and since he has been able to see the world in mathematical terms, which I think is a really valuable skill to have, because we have a different perspective and a different way of looking at things, and we can see things in terms of systems and optimization and all of these different math terms. It just helps us have another way of solving problems.
Yeah, so that's something that we can all definitely have in common, is this appreciation for mathematical thinking and the beauty of math. So we did get to sit down and talk with Dr. Johnson. We learned about everything from his path to mines to his presidential philosophy, and along the way we got some really, really good advice that we really want to share with you. So we subtitled this The Guru because we walked away from that. I went home to my roommate and I was like, oh my gosh, I think I have a new role model, because we took away so many really important pieces of advice that apply to minds and to the world around us that we hope to share with you today as well.
So we'll start off with his presidential philosophy. He told us that he hasn't been asked this question before, so we're really excited to share this like breaking news with him. So he said that first of all, he sees himself as a servant to the institution. So he wants to help the students here to get the most out of minds, and to develop and be ready for life. And he feels the same obligation to the faculty. Something that we really liked that he talked about was helping people pursue what they're passionate about. So he wants to find the passionate people at Minds, which hopefully is all of us, and help us pursue what we really are love.
Yeah, he says that he wants to extend this pride he has to say, yes, I'm from Colorado School of Mines to the rest of us. We want to walk away from our experience here and be so proud to have come from such an incredible institution. And I mean, spoiler alert, I think he's doing a great job. So part of that advice was having it be okay to fail, not being worried about failing, doing what you love, pursuing these opportunities that don't necessarily check the boxes on your life path. Having faith that whatever you do will come back around. Dr. Johnson said that he never planned to do any of the things that he's done. He just had these opportunities come up and he's evaluated the opportunities, said something like, will I ever have this opportunity again? Am I ever going to be able to be the president of this incredible university ever again? No, so of course I'm going to do it. And I think that that's something that we can all think about on a daily basis is, this might not follow my path, but am I going to learn from it? Am I going to experience something from it?
Yeah, and if we are always doing something that we love, then how can we complain? So another great piece of advice that we took was to challenge complacency. So I think at an institution like Minds, we've gotten here by evolving and changing and keeping up with the times. But there's a tendency to get complacent and say, essentially, if nothing's broke, why fix it? So he really encouraged us to challenge the way that just Minds operates, and not necessarily change everything, but just evaluate how everything is working and see how we can make it better.
Yeah, we talked about widening the sidewalks, and so that really combined well with his passion, or with him seeing other people's passions as something that they should pursue, is saying, yeah, I could just be an ex-engineer, but I'm also interested in this, and I'm also interested in this, and being able to combine all of those passions into one route is part of that challenging of complacency that we want to do here. Yes.
So widening the sidewalks is a metaphor.
It is a metaphor.
Okay, I'm not going to literally widen the sidewalks.
Sometimes. But
Okay.
part of that challenging of complacency and being good at that and doing it effectively is also being able to communicate effectively. There's so much importance in having communication skills and being a good team player. And Dr. Johnson really talked about how important that is, and that that's something that the companies that are hiring people from Minds really value about Minds students, is our ability to work in teams. And so questioning how we get those skills and what we can do to strengthen that path as well, super important.
Definitely. Minds creates some really, really great and powerful, essentially, engineers and scientists. And Dr. Johnson told us that we have the power and the responsibility to change the world. So this was one of our favorite quotes from him when we were asking him kind of about the responsibility of the Minds graduate in this ever-evolving world. So he said, it's not just about what new gizmo is going to change our life, whether it's the iPhone 100 or whatnot, but it's the information that you create that stimulates the dialogue that moves things in a different direction. And he said that most other people see problems, where engineers and scientists will see solutions. So Izzy and I like to think of this as our superpower of sorts, and it's kind of our obligation to the world to use this superpower for good.
Yeah. So another mini thing that we learned is that when you talk with people who you really admire and respect, you should take selfies with them. And also one of one of the biggest points that we really took away from our conversation with Dr. Johnson, and one of the things that we really think is important that all of you take away as well, especially in our current social climate, is what Dr. Johnson said was the biggest lesson he's learned in life, and that is to be a good listener before you're a talker. That means to be empathetic, to understand who you're speaking with before you start talking, to understand where they're coming from, be patient with conversations, put in the effort that's required to really understand something before just jumping in. Really, really try to be a good listener. And so I think that that's something that we really want to emphasize today, and something that we really want to thank Dr. Johnson for sharing with us, is that being a good listener really is so important. So yeah, we really wanted to thank Dr. Johnson for having this great opportunity. It was awesome to get to sit down with you, and
yeah, thank you so much for all that you're doing for the institution. We really appreciate it.
And thank you to all of you for listening.
Yes, good and easy, everyone, please. Come back here. It is now my pleasure to introduce Professor Dennis Cook, who's going to join me up here. And Professor Cook, we have an AMS gift for you as our colloquium speaker. Thank you very much for joining us.
Thank you, Paul.
Yeah, and so now you all get to practice your listening as we listen to Dr. Cook. In his own words, tell us about his career. So,
I take it I shouldn't move this because of the cameras?
yeah, sure. That's all right. You can move it when we're done, in case you want to
Thank
move
you.
around in that area.
Thank you.
But I want you to notice our beautiful setting for the interview. This is Colorado Rocky Mountains that I found on Google. Dennis, thank you for visiting us at AMS Colloquium. You're a professor in the School of Statistics at University of Minnesota. You've held several visiting positions and adjunct positions around the world, according to your CV. And you're here to tell us about envelopes in statistics, which we're excited to learn about. According to your CV, on your website, you have 4 books, another in progress, 167 journal publications, and several other research articles since 1972. So my question is, which one is your favorite and why?
Well, first of all, Paul, I'm impressed that you actually counted because they aren't numbered.
I know. It took me a while.
My favorite is always the one I'm working on today.
Okay.
And that's because if you continue to think about what you've done in the past and you continue to grow in your profession and intellectually, you inevitably discover that what you did in the past wasn't quite right. You wished you would have done it differently. And so everything I've done in the past is in some sense flawed, in contrast to what I'm doing now, which isn't.
All right. Well, and what you worked on today was the paper that we're working on with Andrew. So
yes, that's that good. What I'm most excited about today is the work I'm doing with Paul.
Okay. So you recently won the Jack Yoden Award, this is your 3rd, from the journal Technometrics for a paper on statistical experimental design and dimensional analysis. So dimensional analysis is something that all of our engineers learn about and also our applied math grad students learn about. So tell me a little bit about that paper and why it was selected for this award.
Well, first of all, a little caveat. I'm the 4th author on that paper. The first author, Mark Albrecht, was a master's student in statistics. The second author, Chris Knoxheim, was a former student of mine. He graduated in the late 1980s, and he's today, in my opinion, the world expert on, literally the world's expert on computer-generated statistical design. The third author was Tom Albrecht. Tom is an engineer that works for an engineering company in the Twin Cities, and he is Mark's brother. And the 4th author was me. So the idea came about because Chris and I were talking one day about dimensional analysis and how we could make use of that in statistics, and we decided that we should turn a student loose on it. So we jointly advised Mark, and Mark and Chris relied on Tom to keep them grounded in the engineering, and they'd come and talk to me every once in a while when they ran into problems. So I'm kind of the tail on the dog in this particular case. The reason that we decided this might be an interesting project is because in statistical design, particularly optimal design, the tradition has been to just take what the engineers or scientists give you and design an experiment in that context. we had never before thought about using dimensional analysis in the context of experimental design, particularly when you wanted designs where things were scalable. So we tried to bring dimensional analysis into the context of statistical design. Part of it fit really, really well, and part of it didn't fit so well at all. In statistics, we're used to dealing with models that may not be correct. They might have little problems here and there. But when you deal with dimensional analysis, you kind of have to have things really pinned down, or you're in trouble. So all of those issues made for an interesting context and an interesting paper. Now, why it was awarded the Uden Award, you'd have to talk to the people that do that sort of thing.
I'll call them. I'll get back to you.
Call them, yeah.
So your undergrad is actually in math.
Yes.
And so in your opinion, what is the role of math in statistics, and what makes statistics distinct from a branch of applied mathematics?
Well, as I listen to the two young ladies up here talking about enthusiasm in math, I want to make it clear that I did not major in math because of enthusiasm for mathematics. I started, between my sophomore and junior years in high school, I started working at an agricultural experiment station to make money to customize my car, because at the time, hot cars attracted girls and elevated your social standing. So I worked at the agricultural experiment station for 3 more years, part-time during high school. And part of my job was to learn statistics, literally to learn statistics and apply it in an experimental context. After high school, I went to the military. And one of the things I developed in the military was a dread of lines. So when I got out of the military and decided to go to take my undergraduate degree, I still hadn't decided what I was going to major in. But when I walked into the auditorium, at the time there were no computers, you didn't register online. You had a huge auditorium with tables around the edge and different departments represented by the tables. When I looked around and saw long lines everywhere except mathematics, that's what made my decision. So I majored in mathematics, and all the time I was studying math in college, I was still working at the experiment station and still learning more and more and more statistics. And by the time I finished my degree, I was actually running a substantial part of the stat program at the experiment station. And one of the things that I discovered was how math reinforced what I was doing in statistics, and how statistics brought the mathematics that I was learning in college alive. And so that's what I think the connection is. That math reinforces statistics, they give you the tools that you need, and that statistics actually brings the mathematics alive.
So when you said you were afraid of lines, I was afraid you meant linear models. And as a statistician, you can't be afraid of linear models.
No, you can't, that's right.
Last question, what sorts of things do you do besides statistics?
What sorts of things do I do besides statistics? I water ski in the summer, absolutely every chance that I get. I've been doing that for years, and I still do it. I have 2 sons, they're in their 40s, they water ski with me. I have 4 grandchildren that water ski with me. And one of my favorite things in the summer is to get both of my sons, my grandson, and me skiing behind our boat at exactly the same time.
Cool.
So I love to water ski. I have an old MGB that I work on, and I like to drive, I like woodworking, and just tons of other things.
All right, well, thank you so much for being interviewed. Yeah, please clap. I will just move this.
Where is the clicker?
That, and this is here. And Professor Dennis Cook.
What I'm going to talk about today, as you can tell by the title, is something called envelopes. Envelopes are a new idea in statistical modeling, and how in statistics we can separate the signal from the noise. In very, very broad terms, one of the main problems in statistics is to always try and separate the signal from the noise, preserving just the signal while characterizing where the noise arises and accounting for the noise. But that's very, very often a difficult thing to do, because in our efforts to make sure we don't lose signal, we end up preserving noise in the signal that we're trying to grab. Envelopes is a way of capturing the signal and separating out more of the noise. One of the things that we've learned with envelopes is the gain in efficiency that one can get with this methodology can sometimes be absolutely massive, equivalent to taking literally thousands and thousands of additional observations, as I'll show you in a simple example as we go along. So to start with, to emphasize my agricultural roots, we're going to talk about cows. So we're going to talk about the cattle data. There's a type of infestation that happens in cows that's called the stomach or the gut worm. And what happens is this worm gets into the stomach of the cows, passes through, and a cycle is built. Now, the effect of the worm in the cattle is to reduce the weight, costing the farmer or rancher money. It also makes the cows anemic, they can look sickly, and in extreme cases, they can die. So controlling this infestation, this gutworm, is an important part of a farmer's responsibility. So in this case, an experiment was conducted to compare two treatments. 30 cows were selected at random for each treatment, and the treatments were applied. Then the weight of the cow was measured, as you can see there at the bottom, at weeks 2, 4, 6, every other week up to week 18, and then finally a 1-week interval at week 19. Now, the questions that the experimenter wanted answered are, do the treatments have a differential effect, and if so, about when does it first appear? They never expected that applying these treatments, the cows would instantly gain weight. There would have to be a period of time where the worm was controlled and the cow's weight recovered. So there was going to be a lag between application of the treatment and seeing the effects of that in the weight of the cow. So let's first of all look at a plot of the data. So here's a profile plot. Every line on that plot represents an animal. The dots represent the weight at the weeks given along the horizontal axis. The two colors, red and black, represent the two treatments. Now, if you look at that, it looks like kind of a mess. It doesn't look like much is going on. In these kinds of plots, they're good for seeing clusters of points, but here, it doesn't appear that much is happening. Each treatment is kind of intermixed with the other. One way we can handle this with a kind of trivial statistical model, but nevertheless a first step, is to model it as a multivariate linear regression, where y represents all 10 responses for a particular cow. Alpha is an intercept, beta is the differential effect of the two treatments, x is an indicator taking values 0 and 1. The standard estimator of beta, maximum likelihood if you're assuming normal errors, is just to take the difference between the two treatment means. So if we do that, we get another profile plot of just the treatment means. So we have two lines, one marked with red circles, which represents the red treatment, the other line not marked, which represents the black treatment. Now, the question was, that the investigators wanted answered, are these treatments different? And if so, when is the difference first manifest? One of the ways we could address that question simply is to do t-tests at each particular time point and see if there's any significance. Standard first technique in statistics. Well, if we do that, the maximum t-statistic is only about 1.3, maximum over the 10 t-statistics, and I think that's maximum absolute value, is only about 1.3. There's no indication that anything is going on here. And indeed, it's very, very hard to find, using classical methods, if anything is happening between these two treatments. But it is, in fact, possible to see what's going on. And we do that by asking the question, are there linear combinations of the treatments whose distribution does not depend on the treatment? Are there linear combinations of the responses whose distribution is invariant under changes in x? If there are such linear combinations, then that represents a source of variation that we haven't accounted for. If we look at these two curves, we can see how that might come about. The change in mean for each treatment between week 2 and week 4 looks to be about the same. Similarly, the change in treatment between week 4 and week 6 looks to be about the same. So it's conceivable, but there are linear combinations of y whose distribution does not change under changes in x. So this is how the idea for envelopes got started. Are there linear combinations of a response vector that do not change under treatment. The next thing that we have to do is we have to make this a little bit more formal. This is kind of the idea where things got started, but to actually put it into practice, you have to be clear what you mean by linear combinations that don't change with x. So that's what we're going to do next. So formal definition, and now I'm going to pass to a general multivariate linear model, not the specific one we looked at before, but a general one where we have an r by 1 vector of responses, an r by p matrix of coefficients, and a p by 1 vector of predictors. So this is the general model that we're going to be thinking about. The errors will still assume they're normal for the time being, and the data are going to be xi, yi for I equal 1 to n. Now when we're thinking about linear combinations of the response, if we have a linear combination of the response and its distribution is invariant under changes in x, then if we multiply that linear combination by any full rank linear transformation, we're going to get another set of linear combinations that are also invariant under changes of x. And that lack of uniqueness of the linear combination leads one immediately to consider subspaces. So what we're going to do to formalize that intuition we had before is we're going to consider a subspace E so that two things happen. Now in this series of equations, ignore the blue for now. I'll come back to that and just think about the black. So the first thing that has to happen is if I take a response vector and project it onto the orthogonal complement of that subspace, then the distribution of this quantity does not depend on the value of x. So here we have a quantity whose distribution does not depend on the value of x. The second condition we need is we need to make sure that this quantity is not affected by the direct projection onto the subspace, so that this gains information by virtue of a dependence on this. So we assume that what's left over, the projection onto E, is independent of the projection onto the orthogonal complement given x. Now what these two statements imply is that the impact of x on y is concentrated solely in that projection. So if we can find such a subspace, then we could project y onto that subspace without losing any information about the regression. And that's where the basic idea comes from, and this is the manifestation of the intuition excuse me, provided on the previous slide. Now, what does this mean in terms of the linear model? What this means in terms of the linear model, now looking at the blue statements, is that the span of beta has got to be contained in our subspace. So whatever subspace we pick, it has to contain the subspace spanned by the columns of beta. Additionally, the subspace has to reduce sigma, the covariance matrix of the errors, in the following way. What this means is that this subspace has got to be a reducing subspace of sigma. So the two conditions that we have to have are containment, and the subspace has to be a reducing subspace of sigma. If we get those two conditions in our model, then we have these two conditions, and we can conclude that this projection is the only thing that matters. Now, there might be many subspaces that have this property, so to make things unique, we define the intersection of all subspaces with these properties as the sigma envelope of beta, and we denote it as E sub sigma of B, this B being the span of beta. That's where the name envelopes comes from, and this now becomes the target of the inquiry. So we've talked about the intuition, how this comes about. This is how we formalize the intuition. The next step is to take this bit of formality and incorporate it in the model itself and see what falls out. So here we have what falls out. Now to incorporate that bit of formality into the model, we're going to turn to bases. And here we have gamma and gamma 0 are bases for this space and its orthogonal complement. Then the envelope model becomes y is alpha, gamma times eta. Gamma is a basis for the space. Eta are the coordinates of beta in terms of the subspace. And here we have a representation for sigma in terms of bases for the two subspaces. Once we have this model, in good statistical tradition, we can now set out to estimate using any method you'd like. Here we're going to think about estimation via maximum likelihood. We'll determine the dimension of the subspace by using standard off-the-shelf methods, AIC, BIC, likelihood ratio testing, and a whole host of methods that are available for that. Since I'm using off-the-shelf methods to determine the dimension of the subspace, I'm not going to be talking much about how we did that. Now, an important point here is that we are still interested in beta and sigma. Even though I've parameterized this in terms of bases and coordinates, I'm not implying that we should suddenly become interested in the bases of the coordinates. We're still interested in the original things in beta and sigma. So we're still interested in those two. They depend on the envelope, but they do not depend on the particular basis selected to represent it. So what we're going to be doing is basis independent, but it does depend on the subspace. Now, we're going to use maximum likelihood estimation. So we ground out all the equations, and what falls out is kind of interesting. Using maximum likelihood, the estimate of our envelope, the subspace, is the argument that minimizes over a collection of subspaces, the log of this plus the log of this. Now, take just a second to define these things. These two vertical hash marks with a 0 mean the product of the non-zero eigenvalues. So it's like a determinant, only we aren't multiplying all the eigenvalues, we're multiplying only the non-zero ones. S is a U-dimensional subspace of RR, so what we're optimizing over is a Grassmannian. These two things are the sample versions of this and the marginal variance of Y. So this is a very easy matrix to compute. This is an easy matrix to compute, but this optimization, at least within the context of my computing skills, is really hard. It's not convex, it has lots of bumps, and one has to work very, very hard to optimize that objective function. I've been working on optimization methods for this objective function for 2 or 3 years now, and the best methods that I've been able to find rely on very, very clever starting values. Rote methods that you just pull off, I have never been able to get to work well, because they always seem to get caught in local minima. So this is a problem that I still regard as outstanding. There's still work to be done, in part because the computations here turn out to be kind of lengthy. Rarely is that the only computation we need to do in a problem. We might want to embed this in other problems where we iterate over computations like that. There might be lots and lots of times. You might have to compute something like this literally thousands of times in a particular problem, depending on how you're approaching the problem. So having very fast and efficient computation for that objective function is essential for this methodology and for extensions of this methodology. So this is one of the outstanding problems, is to get something that's fast and reliable that can solve these kinds of problems in a blink of the eye. Now, once you get the subspace, the rest is trivial. We let gamma hat be any basis for the subspace, pick anything you want. Then beta hat, the estimator of beta, is the projection onto the subspace of the standard estimator, so we just take this and project it. Sigma is constructed straightforwardly. So the rest of the computation is trivial. That's the hard bit. Theoretically, the variance of the envelope estimator, beta hat, the asymptotic variance, is never bigger than the asymptotic variance of the original estimator. You never ever lose asymptotically doing this. You can only gain, and sometimes you'll gain massively. And there's an indication down below one of the times which you'd gain massively. So these are all the details that I'm going to talk about. Details are now over, and we're going to now appeal to intuition to kind of bring this stuff alive a little bit. So here's a simple example. How do envelopes work? What does all the calculations mean in a way that we can visualize it? So we're going to consider a multivariate linear regression with 2 responses. So you can think of this like the cattle data with just 2 weeks, or if you like, you can think that Y1 and Y2 are systolic and diastolic blood pressure, and you're looking at blood pressure in response to the presence or absence of a drug. Okay? So we've got two responses, systolic and diastolic pressure, presence and absence of a drug. So here's the little linear model that we could start with. The parameters are just defined straightforwardly in terms of conditional parameters given various states of treatment or no treatment. The alphas are defined to be the means of the systolic and diastolic blood pressure under one treatment. The betas are the difference between the two means. Standard estimators are constructed straightforwardly just by substituting sample moments. Now, what we want to do is we want to think about how envelopes work in this very, very simple context. So first of all, depending on how our two distributions look, envelopes might not give you much gain. If our two distributions are really, really, really well separated, standard analyses are going to do just fine. You'll be able to do t-tests. They're going to tell you everything you need to know. On the other hand, standard methods have real problems when the two distributions, this would be the distribution, for example, in the presence of the drug. This is the distribution in the absence of the drug. Well, I guess if this is blood pressure, it should be the other way around. Anyway, standard methods have problems when the two distributions get close together. To think about how envelopes work, let's think about making inference on beta 2, which is the mean of Y2 presence and absence of a drug. A standard analysis starts by taking the data. Since we're interested in beta 2, we're interested in things along the horizontal axis, taking the data and projecting it down onto the horizontal axis. So it takes data, projects it down onto the horizontal axis, and if we do that for many observations, we get two distributions represented along the horizontal axis. Those distributions have a lot of overlap. They're different, their means are different, but it might take you a very large sample size to determine that difference. Envelopes work differently. Envelopes first reason that those two distributions differ only along the envelope subspace here. They do not differ along the orthogonal complement. For example, if I take these two distributions and I project them onto the orthogonal complement of the subspace, the dashed blue line, they'll be identical. There is nothing to learn about the difference between those two distributions along that subspace. All the difference falls in that subspace. Envelopes recognize this, and the first thing they do is they say, well, I need to remove the orthogonal complement because there's no information along that direction to tell me about differences between the two populations. So it does that by, instead of projecting the data directly onto the horizontal axis, it says, I first of all project the data onto the envelope, parallel to this one, directly onto the envelope. That gets rid of this variation. It just removes it from the problem. Then it projects it directly down onto the horizontal axis or wherever you want to make inference. If we do that with a lot of data points, what we get are two red distributions. Those red distributions are very well separated, and it's going to be much easier to tell that the means are different. The difference between the red distributions and the black distributions are what represents the gain in efficiency. Now, as always, simple illustrations like this can be misleading, so let me try and be a little bit careful and tell you that in practice, we will not know exactly what the envelope is. We'll have to estimate it. What that does when we estimate the envelope is it causes a degree of wobble to that line. That degree of wobble is passed directly down to these red distributions, and it will spread the red distributions. But the asymptotic result that I alluded to before says no matter how much I spread the red distributions, they will never spread more than the black distributions. Okay? The second thing that I want to draw your attention to is that the envelope here aligns exactly with the second eigenvector of the covariance matrices. That doesn't have to be true in higher dimensions. It only has to be true because we're looking at 2 dimensions. I have a 1-dimensional envelope, and so I pretty much have to align it that way. In higher dimensions, that does not have to happen. So this is not picking eigenvectors per se. Now here's a simple illustration of that phenomenon. This is a set of data. Y1 and Y2 are spectral intensities at 2 wavelengths for high and low protein wheat. There are 50 observations. There are about 25 in each, I think 26 in one and 24 in the other. You can see that the scatter of the data looks generally exactly like the schematic illustration we had. The envelope is represented here. Now, if I did a standard estimator for this problem and looked at the standard errors of the two components of beta, beta 1 and beta 2, those standard errors would be 8.6 and 9.5. And we would conclude that there are no differences anyplace. If I do an envelope analysis, the standard errors turn out to be 0.4 and 0.6. We could ask the question, to appreciate how much this drop is, how much would I have to increase the sample size for the standard estimator to have standard errors equivalent to the envelope estimators that I got with 50 observations? The answer is you'd have to have on the order of 20,000 observations, 10,000 from each of the two groups. If you took 10,000 from each of the two groups, then you're going to end up with standard errors for the standard estimator of about 0.4 and 0.6. So this is a representation of the efficiency gains that one can get with envelope estimators. Here are two plots. These are plots showing what happens if you use the standard estimator. Projecting down, you get two distributions that's hard to tell apart. That's why their standard errors are so big. Over here, you get the envelope estimators first projecting onto the envelope and then down. And here, the envelope estimators are so much tighter than these that they appear as spikes in the scale of presentation here. So this is just a visualization of what we saw numerically a second ago. Now, back to the cattle data. The bottom plot here is exactly what you saw before. These are just the two mean profiles, and I've reproduced the plot so that to remind you what I did. Up here on top are the mean profiles from an envelope analysis. Now, in the envelope analysis, we inferred that u was equal to 5. That means these 10 points don't vary in 10 dimensions, they vary in 5 dimensions. There are 5 dimensions at which those two curves, or 5 directions, if you will, on which those two curves are the same. We also discovered that if I look at the t-statistics based on the envelope analysis, those t-statistics are bigger than 4.1 for I bigger than or equal to 10. Even if you adjust with a crude Bonferroni inequality, this says that those two treatments are different at least after week 10. So we now have an entirely different inference based on exactly the same data, entirely different than what was given by the standard analysis. What I found even more interesting in this data set is look what happened from here relative to here. Now we know that when you apply these treatments, you aren't going to get an instant bang for your buck. There's going to have to be a lag between treatment and manifestation in weight. Look what happened. The envelope analysis squeezed these two lines together up to about week 10. And it said there's really no difference here, which is exactly what the investigators thought. This is not a consequence of modeling. This is just a consequence of how the envelope analysis came out. So they squeezed it together here and actually separated it a bit up here. Let me back up a second. It's a little bit premature. Now here we have 10 responses, so I can't draw a nice simple picture like I did in 2 dimensions. But what we can do is we can plot, for example, 1 week versus the adjoining week and see what that looks like. And when we did that, we found that, again, the distribution of the data, this is for week 12 versus week 14, looks exactly like the schematic representation that I had for 2 treatments. So again, this is support for the idea that envelopes are working exactly as we expected them to work in that particular problem. Now that ends my formal presentation on envelopes. My goal was to give you just the basic ideas. What I'm going to do now is I'm going to transition into telling you a little bit about where we've gone with that basic idea, where people have gone from that basic idea. The first paper I published with Bing Li and Francesca Charmonti in 2010. It was a discussion paper. Then we had a couple of little papers kind of gearing up before the rapid expansion comes down here. So there are things called partial envelope models. If you have some of your predictors that are just there to reduce variance, you might not be interested in their corresponding coefficients. So partial envelope models enable you to concentrate on subsets of the columns of beta. There's a different method, completely different method for doing prediction. There are predictor envelopes. I started this by saying what happens if there are linear combinations of y that are whose distribution is invariant to changes in x. We could also ask, are there linear combinations of x that do not affect y at all, that have no impact on y? That leads to a parallel development called predictor envelopes. You can put these two things together and get predictor response envelopes. So now we can do predictors and responses simultaneously and really drive down the variation. One of the points that I'd like to make about this methodology is it's not competing with anything. Because you can take any standard technique, pretty much any existing technique, and you can build envelopes on top to improve that technique. So it's not as if we're giving you a replacement or suggesting a replacement for anything. What we're rather doing is saying, here's a way of enhancing whatever you might be doing or whatever is standard. And to illustrate that, we have, in 2015, we published a paper on an envelope version of reduced rank regression. Reduced rank regression is just a regression where you put a restriction on the rank of beta. We built envelopes on top of that. Li and Zhang in a JASA paper that's to appear extended envelopes to tensors. So instead of having a vector for y, you can have now a matrix or an array or some higher dimensional object for y. There are Bayesian envelopes that are going to appear soon in the annals. Sparse envelopes already appeared in Biometrica. In 2015, in the Journal of Multivariate Analysis, there was a method called supervised singular value decomposition. If you have information that can guide you on how you should do a singular value decomposition, then it's called supervised singular value decomposition. And it turns out, as they discuss in their paper, their construction led to a version of envelopes. And lastly, I just published a paper on the best I can do right now on fast envelope algorithms.
But that's not the title.
Pardon? No, that's not the
best I could do.
No, that's not the title. That's not the title. That's not the title. So I should be over when?
5 more minutes.
5 more minutes. So all of this primarily has to do with linear models. We have recently, in 2015, we have a JASA paper where we show how you can do this in pretty much any context. So let's suppose that we have an asymptotically normal estimator, theta hat. This happens. Can come from anywhere. And what we want to do is use envelopes to improve that. So the idea is we take theta hat and we represent it as the projection onto some subspace plus the projection onto the orthogonal complement. We want this subspace to operate in the following way. We want all of the signal to be here, and we want this part to be asymptotically independent noise. So this part has mean 0, it's asymptotically independent of this, and it's just noise. Now, how do we find this subspace? It turns out that this subspace is the smallest reducing subspace of the variance in the asymptotic distribution that contains the span of theta. There are a lot of details to fill in there, but this is the basic idea. Now, the advantage of this general methodology is that it reproduces known envelope methods and it applies to generalized linear models. So everything I told you about up to this point would be reproduced from this very general starting point. It links to pre-specified estimators. You no longer have to use MLE. V of theta can now depend on the parameter being estimated plus perhaps nuisance parameters, which means you might have to iterate. And there's recent work, work in progress right now on applying this methodology to Aster models, which are very complicated models for estimating genetic fitness. And at that point, if you're interested in computing, there is, in MATLAB, we've got a MATLAB routine sitting here. Some of the papers you can find at my website. We also have, we're also in the process of building a lot of this into R. Thank you.
Questions for Dennis? Yeah, Bill.
Yeah, I think I find the value question. Is there a relationship between this and principal components? Because it looks like you're looking for the direction that maximizes the variance.
Is there a direction? No, there isn't. Well, the shorter answer is no. There is no connection between this and principal components. The longer answer is there is a connection with the eigenstructure, but we don't look for principal components. The main ones might have nothing to do with anything. So you can, very often we find that the subspaces that matter, you might pull out the second component, the 9th component, and the 36th component. There's nothing to do with principal components per se.
Questions from the audience at home? That was good, huh? Yeah, Bill, please.
So you showed a maximum likelihood estimator. Was that for the normal case, the case of normal errors?
The maximum likelihood estimator was for normal errors, but we also use that in non-normal cases because as long as you have finite fourth moments in the errors, you have root inconsistency and asymptotically normal estimators. So everything is fine. We use that same objective function. Now you can try and develop other objective functions, but it's really, really hard to get one that beats this.
Right. So in other words, even though that's a very difficult one to deal with, it's the only one you have to deal with as long as the errors are reasonably well. That's
right. If you have errors with really heavy tails, fourth moments might not exist, then that isn't going to work. Finite fourth moments, you're in good shape. There is, I'm sorry.
Oh no, go ahead.
There is, when you think about predictor envelopes, one of the things that we discovered is predictor envelopes turn out to be a generalization of partial least squares regression. We've proven that partial least squares actually estimates an envelope, but it's a crude envelope estimator. It's just based on rough moments. If you apply the maximum likelihood version, you get much, much better estimators.
So just in looking at the cattle data problem, when you first put the slide up, I'm not a statistician, but when I looked at that, I thought, they kind of all look the same. They're all increasing their weight, right?
Right.
So after this whole study, what were you able to say about those two particular treatments? Well,
what we were able to say is it was weird. That the two treatments were the same up to week 10. They might have been different before that, but we could tell they were different after week 10. There was a period of time in which one treatment dominated, and then there was a period of time in which they switched, and then there was then at the end they switched again. Let me see if I can go back to that quickly. There. So they're the same up to week 10. That's what the analysis said. After week 10, the red one dominated. They switched here, and then the black one dominated, and then they switched here. All of these switchings are significant. Now, what that says, and the way the investigators reasoned, is that they gave the treatments back here at time 0. Do the treatments wear off? Is that what happened in the switch? Is there something else that was happening? So there's a quandary there. There's a problem that the investigators have to sort out. But we were able to tell them that the problem starts in week 10, and that switching is real. It's not just a consequence of random fluctuations.
Yeah, I mean, it's just hard for me to tell the difference. I mean, those curves look like the same to me. I mean, so I couldn't really distinguish, but I guess it didn't seem clear to me that just that tiny little difference between those curves and that switch is very significant.
If you're a cattle farmer and you have 10,000 head,
Yeah.
and you can apply this treatment and you can get a weight gain of 5 pounds per head, you're now talking about 50,000 pounds of meat. That's a lot of money. So these little differences, while they might not, relative to this range, these seem small.
Yeah.
But if you multiply that over a herd, taking that herd to market, that's a really big deal.
One more question? Yeah.
You alluded to the difficulty of the optimization problem. Beyond it being non-convex,
Right.
what makes it particularly challenging?
The non-convexity.
Just
Well, I mean, if you do slices through it and plot those slices, it looks like this. It looks the same way if you were going to look for just principal components too. But we've already figured out how to solve those problems. And this is a much more difficult problem.
Greg?
Related to this question, so this criterion that you had was something like a log determinant, but you said it's not really the determinant, you just go over the non-zero eigenvalue.
Yes.
How do you determine what's a non-zero eigenvalue?
When you solve that,
Doing numerics, you're going to have
when you solve that, you presume that you know the value of u. The minute you know the value of u,
Which is the dimension.
the dimension.
The number of non-zero eigenvalues.
You presume you know the number of non-zero eigenvalues. So the way you estimate the dimension, the number of non-zero eigenvalues, is you do it for every one, and then you use a statistical technique to sort through those and pick the right one. So, but in the context of just the optimization, you know how many are non-zero. That's the way the optimization works.
All right. Well, with that, let's thank Dennis. Remind you all that we're going to stick around for another hour if you have more technical questions. I know I and my group, we're going to have more technical questions. And now I'm going to preview the next colloquium by doing, nope, hang on, nope, yep. All right, so Friday, December 2nd, we will have Professor Howard Ellman from the University of Maryland, who's from the computer science department, but he's a numerical analyst, so come hear about numerical analysis. And he'll be here, Friday, December 3rd, 3 p.m. I also want to preview the following Friday, December 9th, will be our very first graduate research symposium brought to you by the graduate students in our department. So stay tuned for that because that's pretty exciting. Otherwise, thanks so much for coming to Colloquium, and see you guys in a couple weeks.